Hello learners, welcome to my channel. I am Priyanka Patel and today I am going to explain about adsorption at solid-liquid interface. If you don't know about adsorption at solid-gas interface, kindly go through my previous video. First learn about adsorption at solid-gas interface and then come to this video. Then only you will be able to understand further about this topic. Learning objectives. This video will improve learners' knowledge about adsorption at solid-liquid interface, wetting and detergency, and electrical properties of interface. So start with adsorption at solid-liquid interface. Adsorption of solute from solution can be treated same as that of adsorption at solid-gas interface. So as we have discussed in adsorption at solid gas interface, we can use Freundlich adsorption isotherm or Langmuir adsorption isotherm. So same as that of we can use Langmuir adsorption isotherm to describe adsorption of solute in solution on solid particle. And here in Langmuir adsorption isotherm equation, pressure is replaced with concentration because in solution concentration is having effect on adsorption, not the pressure. So equation remains the same as that of adsorption at gas interface, just P is reduced with the C. So when we plot a graph of Cx by m, now what is Cx by m? Cx by m is C divided by y. So y is equal to x by m, that we have already discussed in previous video. So this is y is equal to mx plus c, and when we plot c divided by x by m versus concentration, we'll have this kind of line. So what is this? This indicates adsorption of strychnine on various adsorbents. So smaller is the graph, higher the amount of adsorption. So this indicates that activated attapulgite is having higher adsorption in comparison to the kaolin. Next topic is wetting. What is meaning of wetting? In laboratory sometimes you may have observed that addition of charcoal or talc in water, it remains floated on the surface of water. Though its density is higher than water, that does not get sedimented in the water solution and they remain floated on the surface of water because they does not get wetted with water. So here we are going to discuss about why wetting does not occur. So if we consider application of wetting is, it is used for preparation of suspension and emulsion, for granule preparation for tablet, for film coating of tablet, and for dissolution of tablet. Wetting is important property. To understand wetting, we have to first understand surface free energy. As we all know that when liquid comes in a contact with the atmosphere, it tries to contract its surface. Why it tries to contract its surface? Because it experiences weaker attractive force with atmosphere. Because less amount of gaseous molecules are available per unit volume of gas, which can produce attraction with liquid molecule, and two liquid molecules will be having higher attractive forces, so it will try to contract its surface. So same happen with the solid molecule. So when liquid droplet is placed over a surface of solid molecule, if it experience attractive force with solid surface, then it will spread over the solid surface and contact angle will be less. But if it experience stronger attractive forces with the liquid molecule, it will remain floated on solid surface. The best example of which is when we place a drop of water over a clean glass surface, it gets spread over a glass surface. But same doesn't happen with the mercury. When we place a drop of mercury over a clean glass surface, it remains as a single droplet. It does not spread over a glass surface because it is having higher attractive forces with mercury molecule and less attractive force with the glass surface. So to improve the wetting, we have to add wetting agent, and wetting agent action is to lower the contact angle between surface and wetting liquid. The contact angle is the angle between liquid droplet and surface over which it is spread. As you can see in this diagram, When theta is equal to 0, it indicates that liquid is completely spreaded over the another surface and there is complete wetting of solid surface with the liquid. And when theta is equal to 180, it indicates that liquid will remain as a droplet and there is no wetting of solid surface with the liquid. This indicates that higher the value of theta, less is the wetting. So this diagram indicates when wetting occur, it is having value theta less than 90. And as value of theta increases, its wettability reduces. So to define the wetting, we can use Young's equation. So in this equation is gamma S is equal to gamma SL, gamma L into cos theta. So cos theta stands for contact angle, gamma L stands for the surface tension of liquid. This is interfacial tension of solid and liquid and this is surface tension of solid. If we use equation for spreading coefficient that we have already discussed in previous video. So this is equation for the spreading coefficient. If we substitute value of equation 1 in equation 2, we will have this equation S is equal to gamma L into cos theta minus 1. We can use this equation for determination of wetting. We cannot directly use Young's equation for determination of the wetting because it contains terminology surface tension of solid and interfacial tension of solid and liquid, and both determination of surface tension of solid and interfacial tension of solid and liquid is difficult. So we can use equation 3 for determination of wetting. Another equation is if we compare equation 1 with equation 4. So this equation indicates work of adhesion. So work of adhesion already we have discussed in previous video. So work of adhesion is equal to gamma L plus gamma S minus gamma SL. So if we compare both the equation 1 and 4, so we will have equation work of adhesion is equal to gamma L into 1 plus cos theta. This equation can also be used for determination of wetting. According to the nature of liquid and the solid, a drop of liquid placed on a solid surface will adhere to it or not. It will define as the wettability between liquid and solid. When the force of adhesion is greater than force of cohesion, the liquid tends to wet the surface and vice versa. A contact angle is lower than 90, the solid is called as wettable. Contact angle is greater than 90, solid is named as non-wettable. And contact angle is equal to 0, it indicates complete wettability. Critical surface tension. The critical surface tension is the surface tension at which a liquid just completely wets a solid, where cos theta is equal to 1. And it can be represented as symbol gamma C. So if we plot a graph of cos theta versus surface tension for a different liquid, and if we extrapolate the value of surface tension when cos theta is equal to 1, the value of surface tension for a liquid indicate critical surface tension of a liquid which is required to wet the surface completely. So accordingly, to reduces the surface tension of liquid, we have to add surface active agent in it and we can improve the wetting of the solid surface. So to improve the wetting of solid surface, the surface active agent which are used are called as the wetting agent. Start with wetting agent. Wetting agent is a surfactant that when dissolved in a water lowers the contact angle and aids in displacing the air at the surface and replacing it with a liquid phase. Solid will not be able to wet it if their critical surface tension is exceed than the surface tension of the liquid. Thus, a water with having the surface tension value 72 dyne per centimeter will not wet polyethylene with a critical surface tension of 31 dynes per centimeter. Based on this concept, we should expect a good wetting agent to be one which reduces the surface tension of liquid to a value below solid critical surface tension. HLB value of wetting agent is in range of 6 to 9 according to the HLB scale. We can use wetting agent to improve the wetting of solid in liquid to prepare stable suspension or for formulation of granules. Next topic is detergents. Detergents are surfactants which are used for the removal of dirt and they have HLB value between 13 to 16. Detergency process involves initial wetting of dirt and surface to be cleaned, deflocculation and suspension and emulsification and solubilization of dirt particle, and finally washing away the dirt. So this mechanism is explained in this diagram. So as you can observe over here, hydrocarbon tail portion of surface active agent get dissolved in the grease. The grease spot gradually break up and covered with a surface active agent. And in this diagram, small bits of grease are held in colloidal suspension by the detergent. So surface is completely free from the grease. This indicates mechanism of detergent. If we consider dirt is present on either glass, fabric or skin. After application of detergent solution which is having HLB between 13 to 16, it gets wetted. So first mechanism is removal of soluble dirt. So it converts dirt in form of solution. When insoluble solid is present, it converted into deflocculated suspension. If oil soluble dirt is present, it is converted into emulsion. So finally it produces foam and washing will produces clean surface. Next topic is electrical properties at interface. Practical application of this topic is for stabilization of colloids, stabilization of suspension, and for preparation of flocculated suspension, and also used for stabilization of emulsion. Particles dispersed in liquid media may become charged, mainly by three approaches. First one is if the suspension contains electrolytes. Selective adsorption of a particular ionic species by a solid particles is possible, and that lead to formation of charged particle. So that means if a simple suspension consists of any kind of electrolyte and all electrolytes have tendency to get dissociated into positive and negative ion. So when they get dissociated into ion, if any one of the ion gets selectively absorbed on the solid surface, it produces charge on the solid particle. Another is solid particle can also be charged by ionization of functional group of the particle. In this case, the total charge is a function of pH of the surrounding vehicle. That means if solid particle consists of any functional group, for example, COOH. So ionization of that functional group due to pH of the vehicle can produce charge on the surface of the solid particle. Thirdly, which is very rare, when there is difference between dielectric constant between particle and its dispersion medium, it may produce charge on the surface of the solid particle. Next is electric double layer, which is very important to understand. To understand electric double layer, consider suspension which consists of electrolyte. So this is considered as the solid surface. That means surface of a particle. Consider a spherical surface of the particle and we have taken cross-sectional view of the spherical particle. So this portion which is violet in color, it indicates surface of the solid particle which is spherical in nature. And when electrolyte get dissociated into suspension, cations get absorbed on the surface of the particle. So that cations are represented as layer AA dash, and this cation gives solid surface positive charge, and these are called as the potential determining ion. As excess of cations are absorbed surface of the solid particle, now solution consists of rest of the cation and total anions. This cation will attract anions from the solution, and this cation will also repel further adsorption of cation because same charge will repel each other. So this adsorbed cation will attract anions towards the solid surface. The boundary of this layer is indicated by BB dash. This layer is called as the tightly bound layer. Because of the stronger attractive force, the molecules are strongly bind with the surface of the solid with some of the solvent molecule. These ions having a charge opposite to that of the potential determining ion, which are adsorbed on the surface of the solid, and they are known as counter ion or gigaons. That means over here cations are adsorbed on the surface of the solid, so these are called as the potential determining ion, and these are called as the counter ion or gigaons. Opposite to that is also applicable. If negative ion is adsorbed, they are also called as potential determining ion, and positive ion which are present into the boundary of BB dash, they are called as counter ion or gigaons. The degree of attraction of solvent molecule and counter ion is such that it relatively moves with the surface of the solid particle, and the shear plane becomes BB dash rather than the actual surface AA dash. That's why this portion is called as the tightly bound layer. Potential at BB dash is still positive because fewer number of anions are absorbed in comparison to the cation that are absorbed on the surface of the solid. So in region of BB dash to CC dash, it consists of excess of anions and some of the cations. Still, there is no neutrality in this region. Electrical neutrality occurs after region of CC dash, that is beyond CC dash. Between CC dash to DD dash, there is equal distribution of anion and cation is present into the solution. The electric distribution at the solid liquid interface can be visualized as a double layer of the charge. How? The stern layer, the first layer is tightly bound to the solid surface and contain mostly the counter ion, that is AA dash to BB dash. This region, it contains mostly the counter ion, and as I have explained, the attraction of the solvent molecule and counter ion is such that this layer moves with the solid particle. This is called as the tightly bound layer. The second layer is more mobile and containing more counter ion than co-ions, that is region of BB dash to CC dash. So as I have explained, potential at BB dash is still positive because fewer anions are absorbed in comparison to the cation adsorbed on the surface. Excess of anions are adsorbed in this region and fewer cations are adsorbed. So these two layers are commonly known as the electric double layer, that is from AA dash to CC dash. That's why it is called as the diffuse double layer or electric double layer, because this region is diffusible in nature. That's why it is also called as the diffuse double layer. The thickness of double layer depend upon type and concentration of ion in a solution. It is important to note that suspension as a whole, it is electrically neutral despite the presence of unequal distribution of charge in a double layer, because unequal distribution of charge cannot change the concentration of cation and anion. For example, if we consider Na plus or Cl minus, the amount of Na plus and Cl minus is going to remain same in the solution, though distribution will be unequal on the solid surface. So eventually suspension will be electrically neutral. Apart from this, there are two other possibilities also present. So first one is, if we consider same amount of anions absorbed as that of the cation adsorbed on the solid surface, then electrical neutrality will be occur at layer BB dash only. Another possibility is when total charge of counter ion in region A dash to BB dash exceed the charge due to potential determining ion, then net charge at BB dash will be negative and neutrality will occur beyond CC dash. Next topic is Nernst and Zeta potential. So change in a potential as we move from surface of the solid particle, that is from AA dash to DD dash in electric double layer, it can be explained by this diagram. And to describe the potential, there are two different types of potential, Nernst potential and Zeta potential. So difference in an electric potential between actual or a true surface of the solid particle and electroneutral region is referred as surface or electrothermodynamic or Nernst potential. That means the potential at AA dash and electric neutral region. The difference between AA dash to electric neutral region is called as the Nernst potential. Nernst potential is controlled by the electric potential at the surface of the particle due to potential determining ion. The potential difference between shear plane, that is over here, this region, BB dash. The potential difference between shear plane and electroneutral region is known as electrokinetic or Zeta potential. This is called as electrokinetic because this layer is movable and it moves with the solid surface. That's why it is called as electrokinetic potential. Zeta potential. So this indicates three possibilities that I have discussed earlier. Here Zeta 1, it indicates that neutrality occurs at CC dash. Here if we consider AA dash, due to adsorption of cation, it is having a positive charge. As anion adsorb over the cation, it leads to reduction in a potential. But as fewer anions are adsorbed in comparison to the cation, charge is not neutral. Again, in BB dash to CC dash, excess of anions adsorb and neutrality will occur beyond CC dash. So Zeta potential becomes 0 over here. This x-axis indicates distance from surface of the solid particle to the electroneutral region, and this is the potential. Zeta 2 indicates second possibility. That means here if we consider cation are absorbed on the solid surface and if same amount of anions absorbed between A dash to BB dash, then neutrality will occur at BB dash only. In third possibility, cations are absorbed on the solid surface and excess of anions are absorbed in second layer, that is in A dash to BB dash, excess of anions are absorbed. That means amount of anion is more in comparison to the amount of cation absorbed on the surface of solid. So charge will fall from positive to the negative. So at BB dash now, potential will be negative. So in region of BB dash to CC dash, higher amount of cation will be absorbed in comparison to the anion. So that will improve the potential from negative to the positive, and neutrality will be occur beyond CC dash. So this is about Nonce and Zeta potential, and this is useful for development of flocculated suspension because floccules can be prepared by development of control charges on the surface of the solid particle. With this, I conclude my video. These are the references. Thank you for listening my video. If you have any doubt, you can contact me on given email ID. Thank you once again.